Hello, I'm just going to give you a really short introduction to probability. We only need a little bit of it for quantum computing, but we want to make sure we understand it correctly. So let's just look at a popular example of probabilities. You get a prediction about the weather. When I look at my phone, I might see this in the morning. And so for each time of the day, it gives me a probability that it will rain. And so what we want to explore is, what does that really mean? What does a probability of rain at any one moment really mean? So let's see, does it mean it's going to rain at 11 p.m.? Because at 11 p.m. it's 6%? Or does it mean that it's not going to rain at 11 p.m.? Or perhaps that it is going to rain at 4 a.m.? Or does it just mean that it's more likely to rain at 8 a.m. than to rain at 8 p.m.? So it is not a valid conclusion that it is not going to rain at 11 p.m. It still could rain at 11 p.m. The probability wasn't zero. In addition, we don't know that it's going to rain at 4 a.m. It only has a 40% chance of raining. So it might rain, but it might not. Now, is it more likely to rain at 8 a.m. than 8 p.m.? Why, yes. It is in fact more likely to rain at 8 a.m. and 8 p.m. But notice, being more likely still doesn't mean it's going to happen. So this prediction doesn't actually tell us whether or not it will rain on Sunday. So then we have to ask ourselves, what does this information give us? Well, what it says is that given our limited information, because we don't know everything, we don't understand well enough how weather works. If we know what it's like right now, we're not perfect at predicting what it's going to be like later. So given our limited information, if we experienced 100,000, a million, a billion, infinite number of days with these identical conditions, then we could predict, if it were 100,000 days with identical conditions to now, approximately 40,000 of them would have rain at 4 a.m. So I don't know if this particular Sunday will have rain. I just know that less often than half of the time, when I have conditions like this, I get rain at 4 a.m. So when we think about probability, let's first think about things that probability is not. Probability is not actually predicting that something is definitely going to happen or not happen for an individual action, okay? Unless it's at 100% or 0%. So if I have a 75% probability of something happening, that means I don't know it's going to happen. However, what I do know is that if I were to repeat this trial, this test, if the test has a 75% probability of having a certain outcome, that if I try it many, many times, then 75% of those will have that outcome. Right? Likewise, I can't tell whether a prediction, a probability, was correct by the outcome of a single one. If I say that it has 99% probability of something happening, so there's a 99% probability of rain at 10 a.m., and then there isn't rain, does that mean that my probability was wrong? Well, no, this could have been the 1 in 100 that didn't have rain. So we can't tell whether a probability is accurate by just looking at a single trial. We actually would have to do many, many, many identical trials or experiments and see the outcomes of many, many of them to see if our probability was correct. This is very important for quantum because quantum has outcomes that are probabilistic. And so that means that most of the time, we don't know exactly what the quantum outcome is going to be that particular time. We can only tell after many, many times. Okay. So there's a second really important thing about probability for quantum computing, which is that if I have two independent events with their own independent probability, I need to be able to calculate the probability of both events happening, both events not happening, the first event happening but the second event not, or the first event not happening and the second event happening. So I need to be able to take the probabilities associated with independent events and combine them to be a probability of certain combinations of those multiple events. So let's take this as an example. Let's imagine that there's a 50% probability of rain this afternoon. And unfortunately, there's only a 25% chance probability that I will remember to bring my raincoat, because that's just the way I am. So the question is, what is the probability that it will both rain and I will forget my raincoat? Okay. So first we're going to reason this out with sort of a visual representation, and then I'll show you how to calculate it only with mathematics. So we could set this out. So I only have a 25% chance of remembering my raincoat, which is a 1 in 4 chance. So 3 out of 4 chances, 3 out of 4 times, I will forget my raincoat and I'll just have this nice shirt on. And then for rain and shine, it's 50-50. So I have equal probability of each one. Okay. So these are the independent probabilities, and this is a way of visualizing these independent probabilities. Okay. So if we were to say, well, what about raining and jacket? So we could combine these by saying, well, I could have sun, and in the case that I have sun, I have all of these chances, right? 3 chances for shirt and 1 chance for my raincoat. Same with raining. So I can picture it this way, where the first 4 are all in the sun and the second 4 are all with rain. So what I end up having is 8 equally likely non-unique scenarios, 4 of which are sunny, 4 of which are rainy, and 3/4 of which have me in my shirt, and 1/4 of which have me in a raincoat. So I can look at this, I say, oh, 3 of these scenarios have me getting wet in the rain with no raincoat. So out of the 8 total scenarios, 3 of them were the ones I was hoping not to encounter. So that's 3 out of 8, or 37.5% probability. The way you calculate this with mathematics is that you use the original probabilities, 0.75 or 0.25, then 0.5, 0.5. And you lay out all 4 possible combinations. And you just multiply the probability of one happening and the other. So the probability of a shirt is 75%, and a probability of rain is 50%. So I multiply 0.75 times 0.5, and I get 37.5%. And I can look at this for all 4 combinations. So there are 4 unique combinations. And if I add up all my percentages, I could just check to make sure I'm right, or to have one sanity check is just to check to make sure everything adds up to 100%. And it does. And in fact, all the things with the sun add up to 50%. All of the things with the cloud add up to 50%. Everything with the raincoat adds up to 25%. And everything with the shirt adds up to 75%. So that's a way that I can double check my math. So just long story short, if you want to find the probability of 2 events happening, if you have the probability of one of the independent events, you just multiply those probabilities together. So how is probability used in quantum computing? Well, each qubit in superposition has a probability of being measured 0 or 1. That's a single independent probability. It turns out, though, to do any useful computation, you need to use multiple qubits. And so once we combine individual qubits to be multiple qubits working together, that putting them together, we multiply each combination of outcomes by multiplying the probabilities. And then once we have them in those multi-qubit probabilities, then we can do multi-qubit operations and calculate the outcomes.